Welcome to the Deep Dive. Today, we're embarking on a really essential journey into the heart of cybersecurity. Our mission? Well, it's to demystify some concepts that might sound a bit intimidating at first, but are absolutely fundamental to how our digital world stays secure. We're talking about public key infrastructure, or PKI, and a whole range of cryptographic applications, and we'll be pulling our insights directly from a foundational text in this field, Chapter 7 of the CISSP Study Guide. Our goal, like always, is to give you a shortcut to being genuinely well-informed, without feeling buried under a mountain of jargon. We want to spark those aha moments, helping you connect the dots on how everything from your online shopping to global network communication stays protected.
Yeah, and what's truly fascinating here is just how foundational these topics really are. They're kind of the invisible guardians of our digital interactions, right? Whether you're sending a secure email, logging into a corporate network, or, making a purchase online, we're going to explore not just how these intricate systems work, but critically why they're so important, and also the ingenious ways attackers try to break them, along with the equally clever defenses.
Okay, let's unpack this then. Our main source for today's deep dive is indeed the insights from CISSP Chapter 7, PKI and Cryptographic Applications. We're going to look at how robust security architectures are designed and, crucially, how to proactively mitigate their vulnerabilities. Our discussion will center on the core concepts of cryptographic systems, their complete life cycle, from how keys are born to how they're securely retired. And we'll dive into the array of asymmetric cryptographic methods. We'll also cover key management, the power of digital signatures, and those ubiquitous digital certificates you see every day.
Exactly, and we'll definitely spend some time dissecting cryptanalytic attacks, understanding the principles behind these attacks, and, in turn, the protections that well-designed cryptographic solutions offer. Well, that's vital for anyone who wants to be truly well-informed in this space. It's kind of a constant cat-and-mouse game, and knowing the attacker's playbook really helps us build stronger defenses.
Okay, so let's start at the beginning. Asymmetric or public key cryptography. What's the core idea here, especially when you compare it to symmetric cryptography, which some of our listeners might have encountered before?
Yeah, that's a great place to kick things off. If we step back for a second and think about symmetric cryptography, that uses a single shared secret key for both encryption and decryption. It's incredibly fast. Think of it like maybe a shared secret handshake. But it has this one big challenge. How do you securely exchange that secret handshake with someone you've never met over an insecure channel like the internet without anyone eavesdropping? Asymmetric cryptography, on the other hand, it elegantly solves this fundamental problem. It uses a mathematically related pair of keys, a public key and a private key. Let me give you an analogy that might bring it to life. Imagine you have a special, really secure mailbox.
Right.
This mailbox has two slots. One slot is public. Anyone can walk up and put mail into it. That's like your public key. You can share it freely with anyone. They can use it to encrypt a message just for you and drop it in that public slot.
Okay.
But to open the mailbox and actually read the mail, there's a second slot. And that slot has a physical key that only you possess. That's your private key.
Oh, okay, so only I can open it.
Exactly. Anyone can send you encrypted mail using your public key, but only you can open the box and read it with your private key. The public key can be shared freely, while your private key must remain secret and under your control. This design inherently facilitates incredibly secure communication between people who maybe don't know each other beforehand or don't have a secure channel already set up. It's also really scalable, which is a huge plus for big systems like the internet, because you don't need a unique shared secret for every single pair of communicators.
That mailbox analogy really clicks. That makes so much sense. So how does this public and private key pair actually work in practice then? When you're sending a secure message, could you walk us through that flow conceptually?
Absolutely. Let's think of it with a sender. Let's call her Alice, who wants to send a private plaintext message to a receiver, maybe Bob.
Yep.
Alice takes her message and uses an encryption algorithm. But the crucial part here is that she uses Bob's public key to encrypt her message. This turns the plaintext into ciphertext, a jumbled, unreadable mess. Now, when Bob receives this ciphertext, he uses a decryption algorithm. And here's the magic. He uses his own private key to decrypt it. Only his private key, the one that corresponds to the public key Alice used, can successfully turn that ciphertext back into the original message. The real beauty here is that Alice can send an encrypted message to Bob without ever needing to know Bob's private key. She just needs his publicly available one.
Hmm.
Now, an important note, though, is that while public key cryptography is brilliant for secure key exchange and digital signatures, it's computationally much more intensive compared to symmetric crypto.
Ah, okay. So it takes more processing power.
Exactly. It requires a lot more horsepower. Because of this, especially for encrypting large amounts of data, cybersecurity architects often use what's called hybrid cryptography. This approach cleverly combines the best of both worlds. It uses the super-fast encryption of symmetric algorithms for the bulk data, but uses the secure key exchange of asymmetric crypto just to securely share that symmetric key first.
Oh, I see.
So asymmetric crypto handles the initial secure exchange of a smaller, temporary, symmetric session key. Then, that super-fast symmetric key is used for the actual bulk data encryption. It really is the best of both worlds for efficiency and security.
Okay, so given how fundamental this asymmetric cryptography is to, well, nearly everything we do online, what are the most common algorithms we should be aware of? What are the big names?
Right, yeah, this is where it gets really interesting as we dig into some of the foundational algorithms that underpin so much of our digital security. First up, probably the most famous one, Rivest Shamir Adelman, universally known as RSA.
RSA, okay. Heard of that.
Yeah, it's probably the most famous public key crypto system developed way back in 1977. Its security relies on a really clever mathematical problem, the computational difficulty of factoring the product of two very large prime numbers. Think about it this way. It's super easy to multiply two enormous prime numbers together to get a huge number. But if I only give you that huge product, it's computationally virtually impossible to reverse that process and find the original two prime numbers again. This hard problem of prime factorization is what RSA's security hangs its hat on. When you generate an RSA key pair, you're essentially creating these huge prime numbers behind the scenes, and the difficulty of finding them is what keeps your encrypted data safe.
Wow.
Then there was the Merkle-Hellman knapsack algorithm. This was an earlier asymmetric algorithm publicized just a year after RSA. It was based on a different kind of math problem, relying on something called a super-increasing sequence in set theory. It was an innovative early attempt.
But. I sense a but.
Yeah, there's a but.
Yeah.
It's crucial to know that the Merkle-Hellman knapsack system was unfortunately proven ineffective. It was broken back in 1984.
Oh, wow. Okay.
So while it holds historical significance, it's definitely not considered secure for any modern use. It's kind of a good reminder that not all cryptographic ideas stand the test of time and, relentless scrutiny from researchers.
That's fascinating about Merkle-Hellman being broken. So if these algorithms rely on mathematical difficulty, what exactly makes a key strong? Is it just about picking a really, really long number, or is there more to it?
That's an excellent question, and it's absolutely crucial for understanding key strength. The length of the cryptographic key is paramount, yeah? It's this constant balancing act between the level of protection you want and the computational cost, the overhead of using that key. Think about Moore's law, right? The idea that computing power roughly doubles every 2 years. This means that what's considered secure today with a certain key length might not be secure in the near future as attackers get more computational power. So we constantly need longer keys just to stay ahead of this curve.
Right, makes sense.
And furthermore, attackers can now leverage scalable cloud computing resources. They often use powerful graphics processing units, or GPUs, which are incredibly efficient at parallel processing, like number crunching. This lets them attack encrypted data far more efficiently than before, making longer keys even more critical to ensure your data stays protected. When we compare different crypto systems, the required key lengths for equivalent security can vary dramatically. For example, a symmetric key might need 128 bits for strong security, whereas an RSA key needs a staggering 3,072 bits for comparable strength.
Wow, 3,072, that's a huge difference.
It really is. And interestingly, elliptic curve cryptography, or ECC, which we'll get to, can achieve similar security with a much shorter key, maybe around 256 bits. RSA needs such a significantly longer key because the underlying math problem it uses, factoring large numbers, well, it just becomes easier to solve relative to other problems as computing power increases. Moving on, we have ELGMAL, developed in 1985. This algorithm is an extension of the Diffie-Hellman algorithm, which we'll cover in a moment. ELGMAL is used for secure key exchange and can also support message encryption and decryption. Unlike RSA, it was released into the public domain, wasn't patented, so it was freely available. A significant downside of El-Gamal, though, is that the message size actually doubles after encryption.
Doubles.
Yeah, doubles, which means more data being sent over the network, and that can impact performance, obviously.
Right.
And then there's elliptic curve cryptography, or ECC. Developed in the same year as El-Gamal, ECC is based on what's known as the elliptic curve discrete logarithm problem, or ECDLP. Now, the precise mathematical concepts behind ECC are pretty complex, definitely beyond the scope of this deep dive.
Okay, fair enough.
But the important takeaway is its incredible efficiency. For a simplified analogy, maybe imagine points on a curve, like points plotted on a graph but following specific rules. ECC security comes from how incredibly hard it is to figure out how many times you add one point to itself to reach another specific point on the curve. And this addition isn't simple arithmetic. It's a specialized operation defined for elliptic curves.
Okay.
The major benefit is that ECC provides equivalent security with much shorter key lengths compared to RSA. For instance, like I mentioned, a 256-bit ECC key offers comparable security to a 3072-bit RSA key. This efficiency makes it ideal for resource-constrained environments like mobile devices, smart cards, and, low-power Internet of Things, or IoT devices where every bit of processing power and battery life really counts.
So we've talked about how public and private keys are used for secure communication. But what about that initial handshake? How do two parties who've maybe never met or don't have a secure channel, how do they actually establish a shared secret key securely in the first place? It still feels like that chicken and egg problem you mentioned earlier.
That's the perfect way to put it, yeah. And it's precisely where the Diffie-Hellman key exchange comes into play. It's a truly brilliant solution to that very problem. Diffie-Hellman is crucial because it's an approach to key exchange. It's not an encryption protocol itself, right? It allows two partners, even over an insecure channel, to collaboratively generate a shared secret key that only they know, without ever directly transmitting that secret key itself.
Okay, how does that work?
Let's use a popular analogy to make this clear, the paint mixing analogy.
Yeah, it's mixing, okay.
Imagine Alice and Bob want to agree on a secret color without anyone eavesdropping. First, they both publicly agree on a non-secret color, say yellow, everyone knows yellow. Then, Alice secretly chooses her own private color, let's say red. Bob secretly chooses his private color, say blue.
Okay.
Alice mixes her secret red with the public yellow, creating orange. Bob mixes his secret blue with the public yellow, creating green. They then exchange their mixed colors, orange and green, over the insecure channel. An eavesdropper sees the public yellow, and the orange and green mixes, but critically not Alice's secret red or Bob's secret blue.
Right, the original secrets are still hidden.
Exactly. Now here's the magic bit. Alice takes the green she received from Bob and mixes it with her original secret red. Bob takes the orange he received from Alice and mixes it with his original secret blue. The incredible result is that both Alice and Bob will end up with the exact same final shared secret color, maybe a brownish gray in this case, but the eavesdropper, only seeing the public yellow and the two intermediate mixed colors, cannot possibly determine that final shared secret color.
That is clever. Very clever.
It really is. In cryptographic terms, this mixing involves very large numbers and some clever modular arithmetic. Each party picks a secret number, performs a calculation with a publicly known number, and exchanges only the result of that calculation. By doing this, they both arrive at an identical shared secret without ever revealing their individual secret numbers. This shared secret can then be used as a symmetric key for the subsequent, faster data encryption. This approach is commonly used to create shared secret keys in transport layer security, or TLS, the protocol that secures web traffic. You'll often see it referred to as Diffie-Hellman ephemeral, or DHE, or elliptic curve, Diffie-Hellman ephemeral, or ECDHE. The term ephemeral is important. It means the keys are temporary, used only for a single communication session. This provides a highly desirable property called perfect forward secrecy.
Perfect forward secrecy. What's that?
It means that even if an attacker somehow compromises the long-term keys of the server later on, they still can't decrypt past communication sessions that use those temporary ephemeral keys, because those keys were generated for that one session and then thrown away. It protects your past conversation.
That's really important. Okay. But what about all the buzz around quantum computers breaking current encryption? Is that a real imminent threat? or is it still mostly theoretical?
Yeah, this is a cutting-edge area, and it's a very important consideration for long-term cybersecurity. Quantum computing is this advanced field using principles of quantum mechanics like qubits, superposition, entanglement.
Right, the really weird physics stuff.
Exactly. To perform computations in ways classical computers just can't. The concept of quantum supremacy refers to the idea that quantum computers might be able to solve problems currently impossible for even the best classical supercomputers in any reasonable time frame. And this directly applies to the math problems underpinning our current public key crypto, like the factorization used by RSA and the discrete logarithm problems used by Diffie-Hellman and Elgamal. If practical quantum computers become a reality, yes, they could potentially render these popular algorithms insecure.
Okay, that sounds bad.
It does, which is why researchers are actively developing quantum cryptography systems designed to resist quantum attacks. One specific approach here is quantum key distribution, or QKD. QKD uses quantum mechanics principles to create shared secret keys in a way that inherently detects eavesdropping. Any attempt to observe the quantum state disturbs it, alerting the parties. However, it's crucial to understand that while QKD is fascinating research, it's not yet ready for widespread practical use outside of specialized labs and usually only works over relatively short distances currently.
So, not quite ready for securing the whole internet yet.
Not quite yet. The more immediate practical implication of quantum computing for cybersecurity professionals today is the concept of post-quantum cryptography. We need to be aware that sensitive information encrypted today using algorithms like RSA or Diffie-Hellman could, theoretically, be harvested and stored by an adversary right now.
Harvest now, decrypt later.
Exactly. If powerful quantum computers become available in the future, that stored encrypted data could then be decrypted, compromising confidentiality long after the fact. So, the goal of post-quantum cryptography is to develop and standardize new cryptographic algorithms that are fundamentally resistant to attacks from future quantum computers. This is a very active and critical area of research. The long-term security of our most sensitive data really depends on getting this right.
Okay. Shifting gears a bit then, what exactly are hash functions? Why are they so important in cybersecurity? I hear the term hashing thrown around a lot, but what does it really do?
What's really fascinating about hash functions is that they act like unique digital fingerprints for data. The core concept is actually quite simple. They take a variable length message or input, anything from a single character to a massive file, and produce a fixed length output value. This output is universally known as message digest or hash value. Think of it like taking any document, no matter the length, and running it through a special blender that always produces a unique fixed size code, like a short string of letters and numbers.
It's a digital fingerprint, okay. What are they used for?
The primary uses in cybersecurity are crucial for integrity and non-repudiation. First, integrity. They ensure the message wasn't modified in transit. Second, non-repudiation. When combined with digital signatures, they help prove the message came from a specific user. Here's generally how it works. The sender computes a hash digest of their original message. They then transmit that digest along with the message itself. The recipient, when they get both, independently recomputes the hash of the received message using the exact same hash function. Then they compare their newly computed hash with the digest that was sent by the sender. If the two digests match exactly, the recipient can be really confident the message is authentic and hasn't been tampered with. Even the slightest change, a single changed character, an extra space, a missing comma, would result in a completely different hash digest, immediately flagging it as altered.
Right. Any change breaks the fingerprint.
Precisely. Now, for a cryptographic hash function to be considered secure and effective, it needs to meet 5 basic requirements. 1, the input can be any length. 2, the output must have a fixed length, always the same size regardless of input. 3, it must be relatively easy and fast to compute the hash for any input. 4, it must be one-way, meaning it's extremely hard, practically impossible computationally, to figure out the original input message just by looking at its hash output. This property is called pre-image resistance.
You can't run the blender backwards.
You got it. And finally, number 5, critically, it must be collision resistant. This means it's extremely hard to find 2 different messages that produce the exact same hash value. If you can find 2 different messages that produce the same hash, that's a collision, and it fundamentally undermines the integrity check, because someone could swap one message for the other without changing the hash.
Okay, collision resistance is key. So, given these requirements, what are some of the common hash algorithms we actually encounter out there?
Yeah, let's look at the main families you'll see. The first is the Secure Hash Algorithm, or SHA family. These are government standard hash functions promoted by the U.S. National Institute of Standards and Technology, or NIST, for various applications. Within the SHA family, SHA-1 was once very common. It produced a 160-bit message digest. However, due to successful cryptanalytic attacks showing it was vulnerable to collisions. Yeah, NIST officially deprecated SHA-1, web browsers, operating systems, they largely dropped support for it back in 2017. So the key takeaway for you, don't rely on SHA-1 for new secure applications. It's considered broken.
Got it. No SHA-1. What replaced it?
The primary replacement is the SHA-2 standard. This includes several strong variants. SHA-256, which produces a 256-bit digest, is very common. There's also SHA-224, which is just a truncated version of 256. Then there's SHA-512, giving a 512-bit digest, and SHA-384, a truncated 512. These are widely used today and considered secure.
Okay, SHA-2 is the current go-to.
Pretty much. Although in 2015, NIST also released the KEKAC algorithm as SHA-3. This was developed through a public competition to serve as a potential alternative or drop-in replacement for SHA-2. It offers varied hash lengths and can have improved performance and specialized hardware. But while SHA-3 has the same security level as SHA-2, it can sometimes be slower in general software implementation.
So SHA-2 and SHA-3 are both good options now.
Generally, yes. Now, another widely known hash algorithm, though mainly historical for security purposes now, is Message Digest 5, or MD5. Developed back in 1991 by Ronald Ribist, same guy from RSA, MD5 produces a 128-bit message digest. However, and this is a critical point, MD5 is also subject to collisions. It's been proven possible to find two different messages that produce the exact same MD5 hash.
So, also broken.
Effectively, yes, for security purposes like integrity checks or signatures. Therefore, MD5 is absolutely not suitable for ensuring message integrity or for creating secure digital signatures today. You might still see it used for things like checksums for file downloads, just to check for accidental corruption, but not for security against malicious tampering. Avoid it for any new security-critical applications.
Okay, MD5 is out for security. Any others?
Yeah, finally, we have the Race Integrity Primitives Evaluation Message Digest, or RIPE-MD family. These hash functions are used in various places, notably in cryptocurrencies like Bitcoin. Within this family, RIPE-MD 128 produced a 128-bit digest, but has known structural flaws and isn't considered secure. The most commonly used and secure variant is RIPE-MD 160, which produces a 160-bit hash value. There are also RIPE-MD 256 and RIPE-MD 320, though they're less common. The key thing to remember here is that RIPE-MD 128 is not secure, while RIPE-MD 160 is generally considered secure for now.
Got it. So SHA-2, SHA-3, and RIPE-MD 160 are the main secure ones to know.
That's a good summary.
So how do digital signatures tie into all of this hashing and public key magic? What specific problems do they solve that maybe simple hashing or encryption alone don't cover?
Digital signatures are incredibly powerful because they ingeniously combine the best parts of hashing and public key cryptography to achieve two absolutely critical security goals: non-repudiation and integrity.
Non-repudiation and integrity. Okay.
Right. Non-repudiation means the sender cannot later deny having sent a particular message. It's like a legally binding digital seal, proving they originated it. And integrity, as we talked about with hashing, assures you the message hasn't been altered in transit since it was signed. Think of it like a traditional paper document you sign with a pen. Your physical signature proves it came from you, right? And if the document hasn't been tampered with, your signature is still valid.
Okay, makes sense. How does it work digitally?
Let's walk through it again. Say Alice wants to send a digitally signed message to Bob. First, Alice generates a message digest, a hash of her original plaintext message using a strong algorithm like SHA-256, for example. Second, and this is the key part, Alice then encrypts only this message digest using her own private key. This encrypted digest is the digital signature.
So she encrypts the hash, not the whole message, with her private key.
Exactly. Third, Alice appends this digital signature to her plaintext message and sends both the message and the signature together to Bob. Now, when Bob receives this digitally signed message, he does a few verification steps. First, Bob decrypts the digital signature that Alice sent using Alice's public key.
Using her public key, okay.
Right. If this decryption is successful, it immediately confirms that only Alice's private key could have created that signature, which authenticates the origin. Second, Bob independently uses the exact same hashing function, example SHA-256, to create a message digest of the full plaintext message he received. Third, Bob compares his newly computed digest to the one Alice sent, the one he just decrypted using her public key. If these two digests match perfectly, Bob is absolutely assured of two things. One, the message came from Alice, that's authentication and non-repudiation. And two, the message was not modified in transit. That's integrity.
Wow, okay, that covers a lot.
It does. And it's important to remember digital signatures are used beyond just messages. They're widely used to authenticate software distributions like applets or software patches, making sure you're downloading genuine code from the developer. One crucial clarification, though. Digital signatures, on their own, provide integrity, authentication, and non-repudiation, but they do not provide confidentiality. The message itself is often sent in plain text alongside the signature.
Right. So if you want confidentiality too, you'd need to encrypt the whole message separately.
Exactly. You typically encrypt the entire message plus the signature, using the recipient's public key for confidentiality, in addition to signing it with your private key.
Okay. Now, I've also heard of hash-based message authentication codes, or HMX. How do they fit into this discussion about digital signatures? Are they the same thing?
That's a really good clarifying question, and it's a common point of confusion. HMACE is a specific type of message authentication code. You could think of it as a partial digital signature, maybe, but it fundamentally differs from the full digital signatures we just discussed because it uses a symmetric or shared secret key algorithm rather than an asymmetric public-private key pair.
Okay, shared secret key. How does that change things?
Well, HMAC primarily guarantees integrity during transmission. It ensures the message hasn't been altered. It does this by combining the message with the shared secret key and then hashing the result. However, and this is the key distinction, it does not provide non-repudiation on its own. Because it relies on a shared secret key, if two parties share that secret, either party could have generated the HMAC. You can't definitively prove which one signed it just from the HMA itself.
Ah, I see. Because both people know the secret.
Precisely. It can be combined with any standard hash function like MD5, though not recommended, SHA2, or SHA3. So, to recap the difference, HMAC uses a shared secret, making it computationally less expensive than full public key digital signatures, but it sacrifices that non-repudiation aspect. Full digital signatures use public-private keys and give you non-repudiation.
Okay, that distinction is clear now. This gets confusing fast, though, with all the different keys. If I'm using public key cryptography, how do I possibly remember which key to use for what? Encrypting, decrypting, signing, verifying. It seems like a lot to track.
You're absolutely right. That's a common stumbling block. It trips up a lot of people initially, but thankfully there are just 4 simple rules that will help you keep these concepts straight and remember which key to use for which purpose in public key cryptography. If you can master these 4 rules, you'll basically have it down.
4 rules. Okay, I'm ready.
Rule number 1. If you want to encrypt a confidential message that only the intended recipient can read, you must use the recipient's public key. Think of dropping a letter into their public mailbox slot again.
Recipient's public key for confidentiality. Got it.
Rule number 2. If a confidential message has been sent to you and you want to decrypt it, you must use your private key. That's you using your unique key to open your private mailbox.
My private key to decrypt.
Okay, rule number 3. If you want to digitally sign a message that you are sending to someone to provide non-repudiation and integrity, you must use your private key. This proves it came from you, as only you possess that key to create the signature.
My private key to sign.
All right. And rule number 4. If you want to verify the digital signature on a message that was sent by someone else, you must use the sender's public key. This lets you decrypt their signature, which was encrypted with their private key, and verify its authenticity against the message hash.
Sender's public key to verify their signature.
Those 4 rules are really the absolute core principles of how public key cryptography and digital signatures function in practice. If you internalize those, you're well on your way to mastering the essential functionality.
That's actually much clearer laid out like that. Thanks.
No problem. And just quickly, speaking of digital signatures, it's worth mentioning the Digital Signature Standard, or DSS. This is what NIST specifies for digital signature algorithms acceptable for U.S. federal government use. Currently, there are 3 main approved standard algorithms under DSS: the RSA digital signature algorithm, the elliptic curve digital signature algorithm, or ECDSA, and the Edwards curve digital signature algorithm, or EDDSA. All three are robust options for creating secure digital signatures today.
Okay, so we've talked about individual keys and signatures, but what about the whole public key infrastructure? What exactly is PKI, and why do we even need such a, well, seemingly complex system?
That's a great question. So, digital signatures and public-private keys give us trust between individuals, right? Alice can trust Bob's signature, Bob can send Alice a secret message. But what happens when we try to scale that trust up to millions, even billions of users, like the entire internet? How do we build that same kind of verifiable trust on a global scale between people and systems that have never interacted before?
Yeah, how do you trust a random website's public key?
Exactly. That's where public key infrastructure, or PKI, comes in. PKI is essentially the bedrock, the foundation for trusting digital identities in our vast and interconnected online world. It's all about enabling secure communication between previously unknown parties, leveraging the power of public key encryption, but adding a layer of trusted verification. It's basically a hierarchy of trust relationships that combines asymmetric and symmetric cryptography, hashing, and these things called digital certificates to create a robust hybrid cryptographic system. We need it because without a standardized, trusted system for establishing and verifying identities and linking them to public keys, the internet would just be a wild west of trust issues. You'd never know who you were really talking to.
Okay, so PKI is the trust framework. What are its main components? You mentioned certificates.
Right, let's break it down, starting with certificates. Digital certificates are essentially electronic documents like digital identity cards or passports. They provide assurance about communicating parties. They endorse an individual's or entity's public key, proving they are who they claim to be and that the public key genuinely belongs to them. Certificates conform to a widely accepted international standard called X.509, developed by the International Telecommunications Union, or ITU.
X.509. Okay. What's typically in one of these certificates?
A typical X.509 certificate contains several key pieces of information. The version of X.509 it follows, a unique serial number assigned by its creator, the signature algorithm identifier used by the certificate authority to sign the certificate itself, the issuer's name, that's the CA that issued it, a validity period specifying its start and expiration dates and times, the subject's name, which includes details like a common name, maybe a domain name, and a distinguished name with organizational details, and most importantly, the subject's public key, the actual cryptographic key that others will use to encrypt data for that subject or verify their signatures.
So it binds the public key to an identity.
Exactly. It binds the key to a verified identity. Certificates can be issued for various purposes. For computers or machines, like web servers, for individual users, for email addresses, and even for software developers for something called code signing to prove their software is authentic. A specific type you might run into is a wildcard certificate. You might see something like .example.org. This type is valid for all subdomains at one specific level, so it will cover mail.example.org and www.example.org.
But not deeper levels.
Right. Critically, it's not valid for multiple levels, like secure.mail.example.org. You'd need a different certificate for that, or include it specifically.
Okay. And who issues these certificates? You mentioned certificate authorities.
Yes. Certificate authorities, or CAs, these are really the glue that holds the entire PKI together. CAs are trusted third parties. Their central role is to issue, revoke, and manage digital certificates. Think of a CA like a digital passport office. When you apply for a passport, the office verifies your identity thoroughly, right? They check documents, maybe interview you. Then they issue you a physical passport that proves who you are internationally.
Yeah.
Similarly, a CA verifies an entity's identity, whether it's a person, a website, or an organization, and then issues them a digital certificate that digitally vouches for their public key. Others trust this digital passport, the certificate, because they inherently trust the passport office, the CA.
And how do we know to trust the CA?
Good question. Browsers and operating systems come pre-configured with a list of trusted major CAs. Their root certificates are built in. Well-known commercial CAs include names like IdenTrust, Global Sign, Komodo CA, NowSecToGo, GoDaddy, DigiCert, and Trust. There are quite a few. Because this trust is pre-established in your browser, when you visit a secure website, HTTPS, your browser automatically checks the site certificate, sees it was signed by a trusted CA, and establishes the secure connection, usually without you noticing anything beyond maybe a padlock icon. A notable CA worth mentioning is Let's Encrypt. They offer free, automated certificates to encourage widespread encryption use across the internet, making HTTPS much more accessible for everyone, which has been a huge positive development.
Free certificates, that's great. You also mentioned registration authorities. What do they do?
Right. Supporting the CAs are registration authorities, or RAs. These entities assist CAs with the crucial task of verifying user identities before a certificate is actually issued. They often act as intermediaries, handling the initial identity proofing, which can be quite rigorous depending on the type of certificate being requested. They play a vital role in the certification process, especially for validating the identities of remote users or entities. They do the legwork of identity checking.
So the RA checks the ID, the CA issues a certificate based on that check.
Pretty much, yeah. Now, in terms of how this trust is structured, PKI often employs an offline CA and intermediate CAs. An offline CA is the top-level certificate authority, the ultimate root of trust for an organization or system. Its root certificate is kept highly secure, completely disconnected from any networks, literally offline.
Offline for maximum security.
Exactly. It's never used to directly issue certificates to end users or systems. Instead, its primary, very limited role is to create and sign the certificate for subordinate intermediate CAs. These intermediate CAs then serve as the operational CAs, the ones that actually issue certificates for routine operations like individual user certificates or website certificates. This tiered structure, known as certificate chaining or a chain of trust, enhances security and manageability. If an intermediate CA is compromised, you can revoke it without compromising the offline route. When your browser or application verifies a certificate, it actually traces this path of trust back through any intermediate CAs all the way to a known, trusted root CA, one that's built into your system, verifying the signature at each link in the chain to ensure the whole thing is authentic and trustworthy.
Okay, that chain of trust makes sense. So a certificate gets issued. What happens next? How are they managed over time? And what if something goes wrong with the certificate before its natural expiration date? Can it be canceled?
Absolutely, and that's where the certificate lifecycle comes in. It covers the whole lifespan of a certificate and involves several key processes to ensure ongoing trust and security. It starts, obviously, with enrollment. This is the process of actually obtaining a digital certificate. This involves proving your identity to the CA, or RA. Like we said, identity verification can be rigorous physical appearance, documentation, checking credit report data, sometimes verification by trusted community leaders. Once your identity is verified, you typically generate your public-private key pair and then submit your public key along with identity information to the CA in a certificate signing request, or CSR. The CA then double-checks your verified identity, signs your Expert Fire 9 digital certificate with its private key, the CA's private key, and gives you back the signed digital certificate containing your public key and identity info. There are different levels of validation the CA performs too. Domain validation, or DV, is the simplest, just verifying basic control over a domain name, often via email or DNS record. It's quick and cheap, often automated. Extended validation, or EV, certificates offer a much higher level of assurance. They require more rigorous checks to verify the certificate owner is a legitimate legal entity or business, often involving checking official business registrations. These EV certificates used to trigger a green bar in browsers, though that visual indicator is less common now.
Okay, so enrollment and validation. What about checking if a certificate I receive is actually valid?
Right. The next critical step is verification. When you receive a digital certificate from someone, maybe when connecting to a website, your system needs to verify its authenticity. This is primarily done by checking the CA's digital signature on the certificate using the CA's public key, which is usually pre-trusted in your system. There's a quick checklist for verification. First, confirm the CA's digital signature is authentic. Second, ensure you actually trust that CA. Third, check if the certificate has been revoked. We'll get to that in a sec. And fourth, confirm the certificate actually contains the data you expect, like the correct domain name you're trying to connect to.
That last one seems important, making sure the certificate is for the right site.
Absolutely. And a subtle but extremely important point here is about identity. Just having a name like Bill Jones in a certificate doesn't verify identity on its own. It's the CA vouching for that identity, often along with verified address and organizational details that provides the trust. This trust in CAs is paramount. There was a significant security failure back in 2017 involving Symantec, which was a major CA then. They were found to have issued several digital certificates that didn't meet industry security standards. This led Google and other browser vendors to distrust Symantec-issued certificates, eventually forcing Symantec to sell its certificate-issuing business. It really underscores why the integrity and trustworthiness of CAs are so critical to the whole system.
Wow, yeah, that's a big deal.
It was. Another security measure related to verification is certificate pinning. This is where a browser or application is specifically instructed to pin or associate a particular certificate, or maybe just its public key, to a specific host for an extended period. If, during a future connection, that host presents a different, unexpected certificate, even if it's technically valid and signed by a trusted CA, the browser or app will raise an alert or block the connection. This helps prevent man-in-the-middle attacks where an attacker might try to present a fraudulent certificate.
Okay, pinning adds an extra layer. Now, you mentioned revocation. What if a certificate is compromised or needs to be invalidated before its expiration date? How do we stop trusting it?
This is absolutely crucial. A certificate might have a validity period of a year or more, but things can go wrong. The private key might get stolen, the information might become outdated, the entity might cease to exist. So the certificate authority needs a mechanism to revoke a certificate before its natural expiry.
Makes sense. What are common reasons for revocation?
Several common reasons. Maybe the certificate was compromised, the private key was accidentally disclosed or stolen. Maybe it was erroneously issued by the CA in the first place. Perhaps the details in the certificate changed, like the subject's name or organization. Or the security association changed, for instance. The person or organization sponsoring the certificate is no longer employed or affiliated. When a valid revocation request is made, there's usually a maximum response time, a kind of grace period defined in the CA's policy, within which they promise to perform the revocation and make that information public. These practices and policies are typically detailed in a document called a Certificate Practice Statement, or CPS. This outlines exactly how the CA operates when issuing, managing, and revoking certificates.
Okay, so how do systems actually check if a certificate has been revoked? What are the techniques?
Right. There are three primary techniques used today to verify authenticity and, importantly, identify revoked certificates. The first and oldest method is using certificate revocation lists, or CRLs. These are literally just lists published periodically by the CA containing the serial numbers of all the certificates that have been revoked and are not yet expired. Browsers and applications would download these CRL files periodically, say daily, and check the serial number of any certificate they encounter against the relevant CRL.
Okay, simple enough. But downloading lists sounds like it could be slow or outdated.
Exactly. That's the major disadvantage of CRL's latency. There's an inherent delay between when a certificate is actually revoked by the CA and when user systems download the updated CRL. During that window, a compromised certificate might still be trusted. Plus, these lists can get very large, consuming bandwidth.
Right, so what's better?
The second technique, developed to solve the CRL latency problem, is the Online Certificate Status Protocol, or OCSP. OCSP provides much closer to real-time certificate verification. Instead of downloading a huge list, when a client encounters a certificate, it sends an OCSP request directly to the CA's OCSP server, often called a responder. This request essentially asks, hey, what's the current status of certificate serial number XYZ? The OCSP server immediately responds with the certificate status, usually good, revoked, or sometimes unknown. This real-time lookup significantly reduces the window of vulnerability compared to CRLs.
Okay, real-time sounds much better. Any downsides to OCSP?
Well, it can create a potential privacy issue as the CA now sees which certificates and thus potentially which websites a user is checking. It also increases the load on the CA's OCSP servers as they have to respond to potentially millions of individual requests.
Okay. Trade-offs. Is there a third way?
Yes. The third technique, designed to improve performance and reduce the burden on OCSP servers, is certificate stapling, sometimes called OCSP stapling. This is basically an extension of OCSP. Instead of every client needing to contact the OCSP server for every certificate it sees, the web server itself proactively obtains a signed, time-stamped OCSP response for its own certificate from the CA. Then, when a client connects, the web server sends or staples this prefetched signed OCSP response along with its own certificate directly to the browser during the TLS handshake.
So the server does the OCSP check for me and gives me the proof.
Exactly. The browser sees this stapled timestamped response, verifies the CS signature on it, and immediately knows the certificate status is current, or was very recently, without needing to make its own separate OCSP request. This dramatically reduces the number of requests hitting the CA's infrastructure and improves browsing speed and privacy. The web server just needs to periodically refresh its stapled response.
Okay, stapling sounds like the most efficient approach then. Are there different ways these certificates are packaged or stored? I feel like I've seen various file extensions like .crt, .pm, .pfx.
Yes, absolutely. Digital certificates are stored in a variety of file formats, both binary and text-based, which can indeed lead to some confusion with those extensions. Let's quickly break down the most common ones you'll encounter. The first is Distinguished Encoding Rules, or DER. This is a common binary format for X.509 certificates. Binary means it's not human-readable in a text editor. You'll typically find DER certificates with file extensions such as .data, .crt, or .sara.
Okay, DER is binary. What about text?
Right. Next, we have Privacy Enhanced Mail, or PEM. This is essentially an ASCII text version of the DER format. It's base 64 encoded binary data wrapped with plaintext headers and footers. PEM certificates are often stored with .p or also .crt extensions. It's important to note that the .crt extension can be used for both binary DER certificates and text-based PEM certificates. So you can't always tell the format just by looking at the .crt extension. Sometimes you have to actually open the file and see if it's readable text, starting with begin certificate.
Ah, okay, .crt can be tricky.
Any others?
Yes. Then there's Personal Information Exchange, or PFX, format. This is a binary format commonly used by Windows systems. Its main purpose is to store a certificate along with its corresponding private key and potentially the certificate chain, all bundled together in a single, usually password-protected file. You'll usually see PFX files with .pfx or .p12 extensions. These are often used when you need to export a certificate and its private key from one system to import it into another, like moving a web server certificate.
So PFX P12 includes the private key. That sounds sensitive. It is, which is why they should always be password protected and handled very carefully. Finally, P7B, or sometimes PKCS Text7 format. This is another format primarily used by Windows systems. It's an ASCII text format and usually uses the .p7b file extension. P7b files typically contain a collection of certificates, often the entity certificate plus the intermediate CA certificates in its chain. However, P7b files generally do not include the private key.
Okay, so DER, binary, PEM text, PFX P12, binary bundle with private key, and P7B, text bundle without private key. Got it.
That's a good summary. Understanding those distinctions is important for managing certificates correctly, especially when you're installing them on different types of systems or applications that expect a specific format.
Managing all these keys and certificates sounds incredibly complicated and really critical to get right. What are the best practices for handling asymmetric keys to ensure their security over the long haul?
You're absolutely right. All this incredible power that comes with asymmetric keys and PKI really hinges on one crucial thing: how well we manage those keys. Because even the strongest algorithm in the world is useless if the private key falls into the wrong hands, right?
Right.
So good key management is absolutely essential for maintaining the long-term security and integrity of your communications and digital identities. Let's cover some key best practices. First, algorithm selection. Choose your crypto system wisely. Like we touched on, don't rely on security through obscurity. Don't think some obscure or custom algorithm is secure just because attackers might not know it. That's a fallacy. Instead, always choose algorithms that have been thoroughly vetted, publicly scrutinized, and peer-reviewed by industry experts. Stick to the standards.
Okay, use well-known vetted algorithms. What's next?
Second, key length. We discussed this earlier, but it bears repeating. The length of your cryptographic key is critical. It's that balance between the security you need and the performance overhead. Always ensure your key length provides appropriate protection against current and anticipated future attack capabilities, factoring in things like Moore's Law and the increasing power of cloud computing for attackers. NIST and other bodies provide guidance on recommended key length.
All right, longer keys for longer-term security.
Third, and this is perhaps the most critical one, private key security. You must never, ever allow anyone else access to your private key. Under absolutely no circumstances should you distribute it, share it, or let another person impersonate you using it. Your private key is your unique digital identity credential, and your ability to decrypt messages meant only for you. Its compromise means a total compromise of your security associated with that key pair. Protect it like gold.
Treat private keys like, well, private keys. Got it.
Fourth, key rotation. Organizations should implement mandatory key rotation requirements. This means regularly changing your key pair, generating a new public-private key pair, and getting a new certificate at an appropriate interval. Even if a key hasn't been explicitly compromised, rotating keys regularly adds an extra layer of security. It limits the exposure time of any potentially compromised key that might have gone undetected, and it limits the amount of data encrypted with any single key.
How often should keys be rotated?
The appropriate interval depends on the sensitivity of the data, the environment, and organizational policy, but typically it might be every 1 to 3 years for things like TLS certificates. Fifth, key backup and escrow. This might sound counterintuitive after stressing private key secrecy, but you should always securely back up your private key. This is crucial to prevent potentially catastrophic data loss if the key file is accidentally lost, deleted, or corrupted. If you lose the private key used to encrypt data, that data might be lost forever. Additionally, organizations often use key escrow or key recovery arrangements. This allows a trusted third party, usually an internal system or designated personnel following strict procedures, to recover keys if needed, for instance, if the original key holder leaves the company or the key is otherwise unavailable. This ensures continued access to essential encrypted business data. Of course, any backups or escrowed keys must themselves be handled with the absolute highest level of security.
Okay, backup and escrow for recovery, but keep them super secure. Anything else?
Yes, finally, a powerful tool specifically designed for key management is the use of hardware security modules, or HSMs. These are specialized cryptographic components. They can be dedicated physical devices like network-attached appliances or PCI cards, or increasingly cloud-based services. Their whole purpose is to provide extremely secure storage and management of cryptographic keys. HSMs perform cryptographic operations inside their secure, tamper-resistant hardware boundary. The private keys often never leave the HSM in plaintext form.
Ah, so the crypto happens inside the secure box.
Exactly. The benefits are huge. HSMs prevent human error in key handling, they protect keys against physical access and tampering attempts, and they often offer very high performance for cryptographic operations due to hardware acceleration. Examples range from personal use devices like a YubiKey, which can act as a mini HSM storing keys on a secure USB device, to large, high-assurance data center HSMs, and like I said, cloud-based HSMs offered as infrastructure as a service, or IaaS, by providers like AWS, Azure, and Google. They really represent the gold standard for protecting high-value cryptographic keys.
HSMs sound like the way to go for serious key protection. Okay, so we've talked a lot about symmetric encryption being fast for bulk data and asymmetric being great for secure key distribution and signatures. How do they actually work together in the real world? It seems like most practical applications would need both.
That's precisely right, and it's where hybrid cryptography truly shines. It's the practical, workhorse approach that cleverly combines the speed benefits of symmetric algorithms for encrypting the bulk data with the robust, secure key distribution capabilities of asymmetric algorithms. It really gives you the best of both worlds, blending efficiency with strong security.
So how does that hybrid process usually work?
The process generally follows these steps. First, an initial secure communication needs to be established between the two entities, and this typically uses asymmetric cryptography. This initial exchange is primarily for things like verifying identities, using certificates, and agreeing on the cryptographic parameters they'll use. Second, during this asymmetric setup phase, a randomly generated, unique, shared secret key is created. This is often called an ephemeral key because it's temporary, only used for this one session. This ephemeral key is then securely exchanged using asymmetric encryption, for example. The sender encrypts the ephemeral key with the receiver's public key.
Okay, use asymmetric to securely swap a temporary symmetric key.
Exactly. Third, once both parties securely possess this shared secret ephemeral key, they then proceed to exchange all the actual bulk data using that shared key with a much faster symmetric algorithm, like AES. And finally, after the communication session ends, that ephemeral key is securely discarded. It's never stored long-term. This discarding is what provides that perfect forward secrecy we talked about earlier. The real beauty of this hybrid approach is that asymmetric cryptography, which is computationally heavier, only has to handle the initial key distribution, encrypting a relatively small amount of data, just the ephemeral key. Then, the much faster, more efficient symmetric algorithm handles the encryption and decryption of the potentially large volume of actual data being exchanged during the session.
That makes perfect sense. Get the security benefits of asymmetric for the key setup and the speed of symmetric for the data transfer. Can you give a common example?
Absolutely. The most well-known and widely used example of hybrid cryptography in action is transport layer security, or TLS. This is the protocol that secures virtually all modern web communications. It's what puts the S in HTTPS in your browser's address bar and shows that padlock icon.
Right, TLS for websites. How does it use hybrid crypto?
Let's quickly walk through a simplified TLS 1.3 connection handshake. First, when you access a website, Your browser and the web server negotiate a cipher suite. This is basically an agreed-upon set of cryptographic algorithms they both support and will use for the session. For example, which asymmetric method for key exchange, which symmetric algorithm for bulk encryption, which hash function for integrity. Second, your browser retrieves the web server's digital certificate and verifies it using the PKI principles we discussed. It extracts the server's public key from that certificate. Third, the browser and server use an asymmetric key exchange mechanism, typically a Diffie-Hellman variant like ECDHE in TLS 1.3, to securely generate a shared secret session key, that ephemeral key. Fourth, once both the browser and the server have independently calculated the same shared session key, they start using that key with a fast symmetric cipher like AES to encrypt all the actual HTTP traffic, the web page content, your form submissions, everything exchanged between them for the rest of that session.
So the asymmetric part is just for agreeing on that session key.
Primarily, yes, in modern TLS. It's also used for authenticating the server via its certificate. And it's important to remember that TLS is the modern secure replacement for the older Secure Sockets Layer, or SSL protocol. While many people still mistakenly say SSL, if you hear that term today, they almost certainly mean modern TLS. TLS 1.3 is the latest, most secure version, and NIST strongly recommends its use. Previous versions like SSL v3.0, TLS 1.0, 1.1, and even 1.2 to some extent have had known vulnerabilities discovered over the years, like the infamous Poodle attack on SSL 3.0 and early TLS.
So always aim for TLS 1.3 if possible.
Definitely. TLS 1.3 cipher suites typically combine a strong bulk encryption algorithm like AES with a secure hash algorithm like SHA-256 or SHA-384 for integrity checks. And crucially, as mentioned, TLS 1.3 mandates the use of key exchange methods like DHE or ECDHE that provide perfect forward secrecy.
Okay, that covers web traffic well. Now, with so many of us constantly using laptops, smartphones, tablets, how does cryptography protect the data actually stored on these portable devices, especially if they get lost or stolen? That seems like a huge risk.
You're absolutely right, Jamie. Portable devices represent a massive attack surface if they fall into the wrong hands, as they often contain highly sensitive personal or organizational data. Cryptography provides really robust solutions for this exact problem, primarily through data-at-rest encryption. The main solutions are full disk encryption, or FDE, or sometimes volume-only encryption. FDE encrypts the entire contents of a device's hard drive or solid-state drive, making all the stored data completely unreadable without the correct encryption key or password.
So even if someone takes the drive out, they can't read it.
Exactly. Without the key, it's just unintelligible garbage. Common examples of FDE solutions include Microsoft's BitLocker for Windows and its related encrypting file system, or EFS, which can encrypt individual files and folders. Apple's Mac OS uses File Vault for full disk encryption. For users who need cross-platform compatibility or prefer open-source options, Veracrypt is a popular and well-regarded tool that provides strong encryption for Linux, Windows, and Mac systems.
Okay, BitLocker, FileVault, Veracrypt, those are the tools. Is there anything else that helps?
Yes, the security of these FDE solutions is often significantly enhanced by a specialized cryptographic chip found on the motherboard of many modern computers, called a Trusted Platform Module, or TPM. The TPM provides secure, hardware-based storage and management of cryptographic keys, including the keys used for full disk encryption. It can securely store the FDE key and release it only after verifying the system's boot integrity. This enables features like secure boot, preventing unauthorized software from loading during startup, and helps prevent attackers from bypassing the encryption by tampering with the boot process or physically removing the drive and trying to access it on another machine. The TPM ensures the encryption keys themselves are protected by hardware, making attacks much harder.
So the TPM chip adds hardware security for the keys.
Precisely. And don't forget smartphones. Modern mobile operating systems, both iOS and Android, have robust enterprise-level functionality built in that supports strong encryption of the data stored on the phone, usually enabled by default these days.
Good to know phones are covered too. What about email? It seems like such a basic application, but there's constantly sensitive information flowing through email. How do we secure that? It feels less secure than HTTPS somehow.
Email security is indeed critical, Jamie, and you're right, it often feels less inherently secure than browsing a website over TLS. While the underlying protocols for sending email, like SMTP, weren't originally designed with security in mind, there are well-established cryptographic solutions to protect email content. Often, simplicity and user-friendliness are key factors in adoption, making the most cost-effective approach one that integrates well with existing email clients. The goals for secure email are the same comprehensive ones we've discussed. Confidentiality, using encryption, integrity, using hashing, authentication, using digital signatures, and non-repudiation, also using digital signatures.
Okay, same goals. What are the main technologies?
One of the most well-known and historically significant solutions for end-to-end email security is pretty good privacy, or PGP. Developed by Phil Zimmermann back in 1991, PGP combines strong public key cryptography with a unique trust model concept called the web of trust.
Web of trust. How's that different from the CA model?
Instead of relying on a centralized, hierarchical certificate authority model like PKI for websites, PGP's traditional model relies on a decentralized approach. You build trust by signing the public keys of people you know and trust, and you can choose to trust keys that have been signed by people you already trust. It creates a distributed network or web of trust relationships. There are both commercial versions derived from the original PGP and open source implementations based on the Open PGP standard, which adheres to PGP principles. PGP uses modern, strong encryption algorithms, hash functions, and digital signature standards. You might see PGP encrypted messages. They often look like blocks of random text starting with begin PGP message. Signed messages might start with begin PGP signed message and include a signature block. Many privacy-focused email service providers like ProtonMail, StartMail, and Tutanota, formerly Tutamail, offer integrated PGP open PGP-based encryption, making it much easier for average users to leverage its security without manually managing keys. There are also browser extensions like Mailvelope that add open PGP capabilities to webmail interfaces like Gmail.
Okay, PGP with its web of trust. Is there an alternative that uses the standard PKI model?
Yes, the other prominent standard for email security is Secure Multipurpose Internet Mail Extensions, or SUMA. SMIME differs fundamentally from PGP in its trust model. It uses standard X.509 certificates for exchanging cryptographic keys and verifying identities. This means it relies on the established hierarchical CA model, the same PKI used for TLS web security. Like PGP, SUMI uses public keys for digital signatures, providing authentication, integrity, and non-repudiation, and symmetric keys, exchanged securely using public key crypto, for confidentiality. SumMIME is widely integrated into many mainstream corporate and enterprise email clients, including Microsoft Outlook, Apple Mail and iCloud Mail, and Google Workspace, formerly G Suite. You often need to obtain and sum a certificate from a CA, similar to getting a certificate for a website, although some organizations run their own internal CAs for employee SMI certificates.
So the key difference is trust model. SMI uses the hierarchical CA PKI, while PGP traditionally uses the decentralized web of trust.
Exactly. That's the core distinction between the two main approaches to email encryption and signing.
Okay. We mentioned SSL earlier as the predecessor to TLS for web security. Is there anything else to say about that?
Just to reiterate, really, Secure Sockets Layer, or SSL, was the original protocol for encrypting web traffic. HTTPS, usually over port 443. However, SSL had critical flaws discovered over time, particularly in SSL version 3.0. It has been entirely superseded by TLS. So while you might still hear people or even see outdated documentation refer to SSL, they're almost certainly talking about modern TLS implementations. TLS is the secure standard now, SSL is deprecated and insecure.
Got it. SSL is history. TLS is now.
Yeah.
I've heard about the onion router or Tor and the dark web. How do these relate to cryptography and secure anonymous communication?
Tor, which stands for the Onion Router, is a fascinating and powerful system designed specifically for anonymous routing of traffic over the internet. Its primary goal is to protect users' privacy and anonymity by obscuring the source and destination of their online communications.
How does it achieve that anonymity?
It uses multiple layers of encryption, hence the onion analogy, and bounces communications through a distributed worldwide network of relay nodes run by volunteers. When you use the Tor browser or connect through the Tor network, your data is encrypted in successive layers. It's then sent through a randomly selected path of at least 3 relay nodes. Each relay node in the path decrypts only one layer of encryption to find out where to send the data next. Crucially, each relay node only knows the IP address of the node immediately before it and the node immediately after it in the circuit. It doesn't know the original source of the traffic, that's hidden by the first node, the entry guard, nor the final destination, that's hidden until the last node, the exit node. This layered routing makes it extremely difficult for any single point in the path or an external observer to trace the traffic back to its origin or link the origin to the destination.
So it breaks the link between who you are and where you're going online.
That's the core idea, yes. And Tor also leverages perfect forward secrecy, or PFS. because each hop within the Tor circuit uses a set of unique, temporary session keys negotiated between the nodes. These keys are discarded after the circuit is closed. This means even if an attacker could compromise the keys of one relay node later, it wouldn't help them decrypt past Tor traffic that flowed through it. Tor allows for both anonymous web browsing, accessing the regular internet anonymously, and also the hosting of anonymous websites, often called onion services or hidden services. These sites have onion addresses and can only be accessed through the Tor network, providing anonymity for both the content provider and the user visiting the site. This collection of onion services is often what people refer to when they talk about the dark web.
Okay, Tor uses layered encryption and relays for anonymity.
Yeah.
Now, this sounds intriguing. Steganography. What's the difference between steganography and cryptography? They both seem to involve hidden messages, right?
Yeah, this is where it gets really interesting because they tackle secrecy from different angles. While both deal with keeping messages secret, their fundamental goals are different. Cryptography focuses on making a message unreadable to unauthorized parties. The existence of the encrypted message itself is usually obvious. You see a block of ciphertext, you know something secret is there, you just can't read it without the key.
Right. Encryption hides the content.
Exactly. Steganography, on the other hand, is about concealment. It's the art and science of embedding secret messages within other seemingly innocuous messages or files, often called cover files. These could be digital images, audio files, video files, even text documents. The primary goal of steganography is to hide the very existence of the secret message, making it appear as if there's no secret communication happening at all. The cover file should look perfectly normal to anyone not specifically looking for hidden data.
So cryptography hides the meaning. Steganography hides the message itself.
That's a great way to put it. Think of the analogy of writing a secret message in invisible ink on a seemingly normal letter. The letter itself looks innocent, contains mundane text, but there's hidden content that only someone who knows how to reveal the invisible ink or has the right steganographic tool and potentially a key can access.
How is the data hidden in digital files?
Common methods often involve subtly modifying the least significant bits, or LSB, of the data within the cover file. For instance, in a digital image, each pixel's color is represented by numbers, for example, for red, green, blue values. Changing the very last bit, the least significant one of these numbers, makes only a tiny, usually imperceptible change to the actual color displayed. You can use these LSBs across many pixels to encode the bits of your hidden message. To the human eye, the image looks unchanged, but hidden within those tiny modifications is the secret data. Similar techniques exist for audio and video files.
Clever. Is steganography only used for spying?
Not at all, though it certainly can be used for covert communication. It also has legitimate uses, particularly in digital watermarking. Companies might embed hidden copyright information or unique identifiers within images or media files using steganographic techniques. If the content is stolen or misused, they can potentially extract the watermark to prove ownership or trace it back to a leak.
Okay, watermarking is a good use case. Now, thinking about where encryption happens, what are the different points where we can apply encryption in a network, and what are the trade-offs between those approaches?
That's a great question about the scope of protection, Jamie. Where exactly in the communication path do we apply the security? We generally talk about two main architectural approaches, end-to-end encryption and link encryption.
End-to-end versus link.
Okay. End-to-end encryption protects communications directly between the two ultimate endpoints, for example, between your client application, like a web browser or email client, and the final server application. With end-to-end encryption, the data is encrypted at the source application, remains encrypted across the entire network path through routers, switches, different networks, and is only decrypted at the final destination application. The encryption is independent of whatever happens on the underlying network links. TLS for web browsing is a classic example of end-to-end encryption between your browser and the web server. Secure messaging apps like Signal or WhatsApp also use end-to-end encryption.
So the data is protected the whole way from my device to the server's application. What about link encryption?
In contrast, link encryption is applied hop by hop at each segment or link in the communication path. Data is encrypted just before it's sent over one network link, say between your computer and your router, or between two routers. Then it's decrypted at the next hop, the router, potentially inspected or processed, then re-encrypted using a different key and sent over the next link. This happens repeatedly at each hop along the path.
So it's decrypted and re-encrypted at each step.
Often, yes. The key difference in terms of security is that end-to-end encryption protects the entire message payload from the original source application to the final destination application. Intermediate network devices, routers, firewalls, cannot read the encrypted payload. Link encryption, however, only protects data while it's traversing a specific link. At each hop where it's decrypted, the data, including potentially sensitive information, might be momentarily exposed in plaintext within that intermediate device. Also, link encryption typically only encrypts the data payload of a packet, leaving network headers with source and destination IP addresses, etc., unencrypted, which could be useful for traffic analysis by an eavesdropper.
Ah, okay. So end-to-end seems generally more secure for the data content itself.
For the content, yes, generally. Link encryption is sometimes used for protecting traffic over specific untrusted links or in military contexts, but end-to-end provides stronger protection for the data against snooping at intermediate points. In terms of the OSI model, link encryption typically operates at the lower layers, like the data link layer, layer 2, or network layer, layer 3. End-to-end encryption usually happens at higher layers, like the transport layer, layer 4, like TLS, session, presentation, or application layer, layer 7, like PGP or
SE.
Okay. What about Secure Shell, or SSH? Where does that fit in? Secure Shell, or SSH, is a prime example of end-to-end encryption. It's a network protocol commonly used to provide secure remote command line access, secure file transfers using SFTP or SCP, and general secure tunneling of other network protocols, replacing older insecure protocols like Telnet, RLogin, and standard FTP. SSH encrypts the entire session between the SSH client on your machine and the SSH server on the remote machine, protecting confidentiality and integrity. SSH2 is the current secure version of the standard, offering significant security enhancements over the older, vulnerable SSH1 protocol.
Okay, SSH is end-to-end. And what about IP security or IPsec? How does that fit into network security, especially for VPNs?
IPsec, or IP security, is a comprehensive security architecture framework designed to provide secure communication directly at the Internet Protocol IP layer, which is layer 3 of the OSI model. It's widely accepted and very commonly used as the foundation for building virtual private networks, or VPNs. VPNs use IPsec to create secure encrypted tunnels over untrusted public networks like the Internet, allowing remote users or sites to securely access private networks.
So IPsec is fundamental to VPNs. How does it work?
IPsec provides a suite of protocols and options for authentication, integrity, and confidentiality of IP packets. It has two main modes of operation. First, transport mode. In this mode, only the payload, the actual data part of the IP packet, is encrypted and/or authenticated. The original IP header remains mostly intact and unencrypted. Transport mode is typically used for securing communications directly between two endpoints, peer-to-peer, that handle the IPsec processing themselves. Second, tunnel mode. In this mode, the entire original IP packet, including its header, is encrypted and/or authenticated. Then this whole encrypted packet is encapsulated within a new IP packet with a new IP header. This effectively creates a secure tunnel between two IPsec gateways, like VPN routers or firewalls. Tunnel mode is commonly used for gateway-to-gateway communications, such as connecting two remote office networks securely over the Internet, or for remote access VPNs where your laptop tunnels all its traffic back to the corporate gateway.
Transport mode protects the data. Tunnel mode protects the whole original packet.
Okay.
What provides the actual security services in IPsec?
IPsec relies on two main security protocols to provide its services. The first is the authentication header, or AH. AH provides strong data origin authentication, proving who sent the packet, connectionless integrity, ensuring the packet wasn't modified in transit, and crucially, protection against replay attacks, where an attacker tries to resend a valid captured packet. AH achieves this by calculating an integrity check value over most of the IP packet, including headers that don't change in transit. However, AH does not provide confidentiality. It doesn't encrypt the data.
So AH is for authentication and integrity, but not secrecy. What about encryption?
That's where the second main protocol comes in. Encapsulating Security Payload, or ESP. ESP is the workhorse for providing confidentiality encryption of the IP packet's payload. It also provides integrity protection for the encrypted payload and offers some level of data origin authentication and anti-replay protection as well, though arguably AH's integrity protection is stronger as it covers more of the packet header. You can technically use AH and ESP together or use ESP by itself, providing both encryption and integrity. Using AH alone without ESP is rare these days, as confidentiality is usually a primary requirement. Most modern IPsec VPNs rely heavily on ESP, often in tunnel mode.
Okay, AH and ESP are the security protocols. How does IPsec manage the keys and settings?
When two systems want to communicate using IPsec, they first need to establish a security association, or SA. An SA is essentially a one-way agreement between the two peers that defines all the security parameters they will use for their communication in that direction. This includes things like which security protocol to use, AH or ESP, the specific encryption and authentication algorithms, the example AE for encryption, SHA-256 for authentication, the cryptographic keys, the key lifetimes, and the mode, transport or tunnel. Since an SA is typically unidirectional, for a normal two-way communication channel, you actually need two SAs, one for traffic flowing in each direction. These SAs are usually established dynamically using a key management protocol like the Internet Key Exchange, or IKE, which securely negotiates the parameters and generates the necessary keys.
Well, IPsec sounds quite involved, but powerful for network layer security. We've covered a lot of traditional and modern applications. Are there any truly cutting-edge uses of cryptography emerging now, maybe still in research or early adoption?
Yes, absolutely. What's really fascinating is seeing how cryptography is constantly adapting and becoming a foundational component for entirely new technologies, often enabling capabilities that wouldn't be possible otherwise. One hugely significant emerging application is blockchain. At its core, a blockchain is essentially a distributed, shared, and immutable ledger. Records, often called blocks, are cryptographically linked together in a chain and stored across many different computer systems in a peer-to-peer network. This distribution and cryptographic linking make it extremely difficult, practically impossible, to tamper with past records without being detected.
Right. The technology behind cryptocurrencies like Bitcoin.
Exactly. Bitcoin was the first major application that brought blockchain into the spotlight. It demonstrated the power of a decentralized system with no central regulator, relying on cryptographic principles like hashing and digital signatures to maintain an immutable public ledger of transactions. But the potential applications of blockchain go far beyond just cryptocurrencies. Think about secure and transparent supply chain tracking, verifying the provenance of goods for consumers, creating secure public repositories for documents or credentials, enabling secure voting systems. Anywhere you need a trustworthy, tamper-evident, distributed record-keeping system, blockchain has potential. Cryptography is absolutely fundamental to its security and integrity.
Okay, blockchain is a big one. Anything else on the horizon?
Another important area is lightweight cryptography. We touched on the need for efficiency with ECC, but lightweight crypto takes this even further. It's specifically designed for devices with extremely low power levels and very limited computing resources. Think of tiny sensors in the Internet of Things, IoT, smart cards, RFID tags, embedded medical devices. Traditional cryptographic algorithms like AES or RSA can be too computationally intensive or energy hungry for these severely constrained environments. Lightweight cryptography focuses on developing algorithms that provide adequate security with very low latency, highly efficient encryption and decryption, and minimal power consumption, making it feasible to implement strong security on even the smallest, cheapest hardware. These algorithms are often implemented directly in specialized hardware circuits to optimize their performance and energy use. NIST has been running a competition to standardize lightweight cryptographic algorithms.
So securing the tiniest devices, that's crucial for IoT. One more.
Yes, one more really mind-bending one, homomorphic encryption. This is a highly specialized and still largely theoretical or niche use case, but with incredible potential. Homomorphic encryption allows computations to be performed directly on encrypted data without decrypting it first.
Wait, you can calculate on data while it's still scrambled? How?
Yeah. It's based on some very advanced mathematical properties. Essentially, the encryption scheme is designed such that applying a mathematical operation, like addition or multiplication, to the ciphertext produces an encrypted result which, when decrypted, matches the result of applying the same operation to the original plaintext. The huge benefit here is for privacy, particularly in cloud computing or other untrusted environments. Imagine you want a cloud service to perform some analysis on your highly sensitive data, like financial records or medical data. With homomorphic encryption, you could upload your encrypted data to the cloud. The cloud provider could then run the analysis directly on the encrypted data and return an encrypted result. You would be the only one able to decrypt the final result to see the findings. The cloud provider performs the computation without ever seeing your sensitive plaintext data.
That sounds like a holy grail for cloud privacy. Is it practical yet?
It's getting closer, but it's still computationally very expensive compared to operating on plaintext or using standard encryption. There are different types: partially homomorphic, allowing only certain operations like addition or multiplication, and fully homomorphic, allowing arbitrary computations. Practical applications are starting to emerge in specific areas, but it's not yet widespread for general-purpose computing due to the performance overhead, but the potential is enormous.
Wow. Okay. Homomorphic encryption. Definitely one to watch. Now, this whole field sounds like an endless cat-and-mouse game between the defenders building these crypto systems and the attackers trying to break them. What are the common ways attackers actually try to crack cryptographic systems? What's in their toolbox?
You're absolutely right. It is a constant cat-and-mouse game. If we connect this back to the bigger picture, understanding the common attack methods is fundamental to designing, implementing, and choosing stronger cryptographic defenses. Knowing your enemy, right? Let's go through some of the most prevalent cryptanalytic attacks. First, the most conceptually simple attack, the brute force attack. This is just what it sounds like. The attacker tries every single possible key or password combination until the correct one is found. It's a trial and error guessing game on a massive scale.
Just trying everything. That sounds slow.
It can be, especially against strong, long keys. The primary defense against brute force is using keys and passwords that are long and complex enough to make the total number of possibilities astronomically large, rendering a brute force search computationally infeasible within any reasonable human time frame, or even geologic time frame for strong keys. However, attackers have tricks to speed things up. For password cracking, they use tools like rainbow tables. These are huge, pre-computed tables containing hash values for millions or billions of common passwords and variations. Instead of hashing each guess during the attack, they can quickly look up a captured password hash in the table to find the corresponding plaintext password.
Pre-calculating the answers. Clever.
It is. Attackers also leverage specialized hardware, particularly powerful graphics processing units or GPUs, which are designed for massive parallel computation. They can try billions or even trillions of password or key guesses per second, vastly accelerating brute force attempts compared to using a standard CPU.
So how do we defend against rainbow tables and fast GPUs for password?
The key defense against rainbow tables for password hashing is using a salt. A cryptographic salt is a unique random value that is generated for each user and added to their chosen password before it's hashed and stored in the database. Because the salt is unique per user, even if two users happen to choose the same password, their stored hashes will be different. Password plus salt 1 versus password plus salt 2. This completely defeats standard rainbow tables, as the attacker would need to generate a separate table for every possible salt value, which is infeasible. Furthermore, modern secure password hashing functions like password-based key derivation function 2 or PBKDF2, bcrypt, and script not only incorporate salts, but also perform key stretching or iterative hashing. They deliberately run the hashing process thousands or even millions of times for each password guess. This significantly increases the computational effort required to check even a single password, making brute force attacks much, much slower, even with powerful GPUs.
Salty and key stretching. Got it. What other types of attacks are there?
Moving beyond pure brute force, we have attacks that look for weaknesses in the system or the algorithm itself. An analytic attack tries to use mathematical analysis, algebraic manipulation, or properties of the algorithm to reduce its complexity, effectively finding a shortcut compared to brute force. An implementation attack, which we touched on briefly, exploits flaws not in the algorithm's theoretical design, but in how it was actually implemented in hardware or software. This could be a programming bug, a weak source of randomness for key generation, or some unintended side effect of how the crypto operation is performed.
So attacking the code, not the math.
Exactly. A statistical attack looks for statistical weaknesses or biases in the crypto system. Maybe the ciphertext doesn't look perfectly random, or certain patterns emerge that can be exploited to deduce information about the key or plaintext. Then there are more physical or environmental attacks. A fault injection attack tries to compromise integrity or induce errors by causing a temporary physical fault in the hardware running the crypto. Maybe using a voltage glitch, a laser pulse, or extreme temperature changes, hoping to cause predictable errors that leak information.
Wow, physical attacks too.
Yes, and related to those are side channel attacks. As we discussed, instead of attacking the algorithm or implementation directly, these attacks observe physical characteristics of the cryptographic process while it's running. They might measure tiny variations in power consumption, electromagnetic radiation emitted by the chip, or the precise timing of operations. Attackers analyze these physical side channels to infer sensitive information, like bits of the secret key, based on correlations between the physical measurements and the data being processed. A timing attack is a specific, well-known type of side channel attack that measures the exact time taken to perform cryptographic operations. For example, if certain operations take slightly longer depending on whether a guess about a key bit is correct or incorrect, that timing difference can be statistically analyzed and exploited to recover the key much faster than brute force.
That's incredibly subtle, measuring power usage to find keys.
It is. These attacks highlight why secure implementation is just as important as strong algorithms. Now let's look at attacks that leverage different levels of known information available to the attacker. Frequency analysis is a classic cryptanalytic technique, often the starting point for a ciphertext-only attack, where the attacker only has access to the encrypted message, the ciphertext. They analyze the frequency of letters, pairs of letters, digraphs, or other patterns in the ciphertext, and compare them to the known statistical frequencies of letters and patterns in a likely underlying language, like English, where E is the most common letter, TH is a common digraph, etc. This can be very effective against simple substitution or transposition ciphers.
Like solving crypto puzzles in the newspaper.
Pretty much the same principle. A step up from that is a known plaintext attack. Here, the attacker somehow obtains a copy of both the encrypted message, ciphertext, and its corresponding original plaintext. Having these pairs can provide much more information about the encryption process and potentially allow the attacker to deduce the key, especially for weaker or flawed algorithms.
How would they get the plaintext?
Maybe they know certain standard headers or footers are always present in the messages, or they trick the sender into encrypting a message the attacker already knows. Even more powerful is a chosen plaintext attack. In this scenario, the attacker can actually choose arbitrary plaintext messages and somehow trick the system into encrypting them and providing the corresponding ciphertext. Being able to select specific plaintext to encrypt allows the attacker to probe the crypto system much more effectively and potentially uncover weaknesses or the key itself.
Okay, choosing the plaintext gives them more power. Is there anything stronger?
Yes, arguably the most powerful type of attack in this category is the chosen ciphertext attack. Here, the attacker not only obtains ciphertext, but also has the ability to get chosen portions of that ciphertext decrypted using the target's decryption key, perhaps by interacting with the system that performs decryption. This ability to selectively decrypt chosen ciphertexts can provide extremely valuable information for breaking the system or recovering the key. Modern encryption schemes are specifically designed to be secure even against chosen ciphertext attacks, often referred to as CCA2 security.
Wow, okay, those get progressively more powerful.
Yeah.
What about attacks involving multiple parties or tampering with communication?
Right. A very well-known network threat is the man-in-the-middle, or MITM, attack. In a classic MITM attack, a malicious individual positions themselves logically between two communicating parties, say Alice and Bob. They intercept the communication attempts and then impersonate each party to the other. So Alice thinks she's talking directly to Bob, but she's actually talking to the attacker, Mallory. And Bob thinks he's talking directly to Alice, but he's also talking to Mallory. Mallory sits in the middle, relaying messages back and forth, but critically, Mallory can read, modify, or inject messages in either direction without Alice or Bob realizing they aren't communicating directly. Strong authentication and certificate validation are key defenses against MITM attacks.
So the attacker is secretly relaying and potentially altering the conversation.
Exactly. It's important not to confuse MITM attacks, where the goal is active interception and modification, with replay attacks. In a replay attack, the attacker simply captures a valid encrypted message, like an authentication request or a command, and then replays it later to the system, hoping the system will accept it again and grant access or perform an action illicitly. Replay attacks are typically defeated by incorporating protections like sequence numbers, timestamps, nonces, random numbers used only once, or using challenge response mechanisms during authentication, or simply by using ephemeral session keys that are invalid after the original session ends.
Okay, replay is just resending old messages. What's a birthday attack? That sounds harmless.
It sounds harmless, but it's actually a significant type of collision attack, particularly relevant to hash functions. It focuses on the probability of finding any two different inputs that produce the same hash output. It exploits a mathematical probability concept called the birthday paradox, which surprisingly states that in a room of just 23 people, there's already a greater than 50% chance that at least 2 people share the same birthday. You don't need 366 people for a good chance of a match. In cryptography, this means that finding any two messages that hash to the same value, a collision, is generally much, much easier computationally than finding a specific message that hashes to a predetermined target value, pre-image resistance. For a hash function with an end at output, a birthday attack can find a collision with a complexity roughly on the order of 2 and 2 operations, rather than the second expected for finding a pre-image. This is why hash functions need output lengths that are significantly longer than symmetric keys for equivalent security against collision attacks. For example, 256-bit hash for roughly 128-bit collision security.
Ah, so the paradox makes finding any collision easier.
Interesting. Any other attack vectors? Well, we should never forget the human element. Social engineering. While not a technical cryptanalytic attack in the mathematical sense, social engineering can be incredibly effective in bypassing cryptographic protections entirely. An attacker might trick a legitimate user into revealing their password, their decryption key, or installing malware that compromises their system, rendering all the sophisticated crypto useless.
The weakest link is often human.
Sadly, yes. And finally, we need to mention how attackers themselves leverage cryptography for malicious purposes, most notably in ransomware. Ransomware attacks use strong encryption algorithms, often implementations of AES or RSA readily available in libraries, to encrypt a victim's valuable data documents, photos, databases, system files, rendering it completely inaccessible. The attackers then demand a ransom payment, usually in difficult-to-trace cryptocurrency like Bitcoin, in exchange for the decryption key needed to recover the data. It's a brutal demonstration of how powerful cryptographic tools can be when wielded maliciously.
Wow, okay. That covers a huge range of attacks. It really is a complex landscape.
Okay.
Alex, that was a truly deep dive. Let's try and quickly recap some of the essential concepts we've covered today. It was a lot to take in.
Absolutely. It was dense, but hopefully clear. So we started way back with asymmetric cryptography, stressing that core idea of using a related pair of public and private keys. We established that your public key is shared freely for others to encrypt messages for you or verify your signatures, while your private key is kept absolutely secret, as only it can decrypt those messages or create your unique digital signature. This enables secure communication without pre-shared secrets.
Right. We then look at key algorithms like RSA, the famous one based on the difficulty of factoring large prime numbers, and the more efficient elliptic curve cryptography, or ECC, which gives similar security but with the shorter, more manageable key lengths, making it great for mobile devices. We also unpack the clever Diffie-Hellman key exchange, that paint mixing analogy, showing how parties can establish a shared secret key over an insecure channel, a technique vital for TLS and enabling efficient hybrid cryptography.
Exactly. We then dissected hash functions, those one-way mathematical blenders that create fixed-size, unique message digests, or digital fingerprints, primarily used for checking data integrity. We covered the important SHA family, remembering SHA-1 is broken, SHA-2 and SHA-3 are good, the definitely broken MD5, and the right AMI-D variants, with RIPEM MD160 being the main secure one. We saw how these hash functions combine with private keys to create digital signatures, giving us those crucial guarantees of non-repudiation, can't deny sending, and integrity wasn't changed. And importantly, we clarified those 4 simple rules for which key to use for encrypting, decrypting, signing, and verifying.
That led us straight into public key infrastructure, or PKI, the whole ecosystem needed to manage digital identities and trust at scale online. We explored its core components: the certificates themselves, X by FISO or 9 standard, the trusted certificate authorities, or CAs, that issue and vouch for them, the registration authorities, RAs, that help with identity verification, and the critical certificate lifecycle. That cycle includes enrollment, verification, and especially the crucial revocation methods used when things go wrong, like CRLs, the old list method, OCSP, the real-time check, and the efficient certificate stapling.
Perfect. Finally, we touched upon best practices for asymmetric key management. The importance of algorithm choice, key length, protecting private keys like treasure, key rotation, secure backup and escrow, and the significant benefits of using hardware security modules, or HSMs, for top-tier key protection. We looked at applied cryptography in various scenarios, protecting portable devices with FDE and TPMs, securing email with PGP, Web of Trust, or SMIME, PKI-based, securing web applications with TLS, hybrid crypto, enabling anonymity with Tor, and the difference between encryption and steganography, hiding existence versus content. We also differentiated end-to-end versus link encryption and covered IPsec for VPNs. And we wrapped up by surveying the landscape of cryptographic attacks from brute force and side-channel attacks to MITM, birthday attacks, and replay attacks, along with the vital defense of salting passwords.
And that brings us to the end of another deep dive. You should now have a much more robust understanding of PKI and cryptographic applications, hopefully with plenty of those aha moments to carry forward into your cybersecurity thinking or studies.
We certainly hope this comprehensive exploration has given you the foundational tools and concepts to better understand, discuss, and maybe even apply these absolutely critical cybersecurity principles. Remember, knowledge is really most valuable when it's not just memorized, but truly understood and put into practice.
Keep listening, keep learning, and until next time, stay curious.